Fracture toughness testing, including J testing, is becoming much more common in the industry than it was, say, 10 years ago or even 5 years ago.
At MMT, one of the big things we are doing is developing non-destructive tools. And to do so effectively, what we need to do is we need those laboratory values so we can confirm the equivalent that we're actually measuring what we expect. So at a really high level, we've got a tool. It measures fracture toughness. That's the intent on it. But where we kind of fell into this area here is that without reliable lab data that we could trust and feel consistently confident in, we started running into some pitfalls here. So what we really did was we have an industry project that we're working on right now, and we've got a bunch of data, right? We're trying to match our data with the laboratory data. And you can see here on the plot on the right, we're doing okay. It's us on the y-axis, it's the laboratory value on the x-axis, and it's a bit scattering. So what we found there was it became very difficult for us to accurately represent the laboratory values.
Essentially, you're looking at the energy spent on the y-axis as a function of how that crack moves forward during that actual loading test. And each data point is taken by loading and unloading that while the crack can move forward. So if you look on the left side, it's a very nice fit. But when you go to the right, you can see that the data suggests the blue data suggests that this material actually is above the curve. Now, one thing important to say is if you say here, I'm underestimating by 5% on this value on the y-axis, that there's J value, when you get to the fracture toughness, which is K, you square that error. So it's actually 10% difference just because of the curve fitting. With respect to crack extension, this is a little bit perhaps hard to situate in space, but we showed the compact tension specimen, and this is the notch. Then you have the pre-crack, and over here you have the track expansion. So it's not perfect here on the left, but it's pretty good, as opposed to the right, where there was a lamination in the center of the specimen, and that crack extension here is really a triangle. Now, there's a lot of other stuff that would have happened, the crack being skewed, the crack being a little bit elliptical, that will affect the testing.
So on our end, the first thing, take a look at the procedures, understand what's going on, understand how they're being tested. Those are some things that we've unfortunately learned the hard way. And I don't want other people to have to learn the hard way there as well. If possible, it's great to be able to test multiple labs, see how they compare to one another, really benchmark there. So that's been something that we've been able to benefit from. It's something that we need to do. And it's something that I think could be beneficial to some other folks going forward. And then lastly on this slide is really keep track of what's going on. Anytime a procedure changes, anytime that, you maybe in the same case that we did, if there is a test that's in the wrong orientation, that might not be leveraged right now, but it could be something that leverages itself later on, depending on what you're analyzing and what that actually looks like.